Alright, welcome back. In this video, we're going to go over E2 practice problems. Let's go. So we got 3 problems asked about Zaitsev, Hofmann, major, minor, and arrow pushing mechanisms for E2. Then we have problems asking about what the correct base you should use is to get the desired product. Dun, 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 dun. And then we have a challenge problem, which is not really a challenge problem. It looks complicated, but it really isn't. Trust me. Now, if you haven't watched my E2 mechanisms video, I highly suggest you do it because it's going to help me out and it's also going to help you out. And I'll put a thing on the screen right now. That's my sound effect. And I'll put a link in the description as well. All right, indicate the Zaitsev and Hofmann products of each reaction, indicate the major and minor products, and then draw the arrow pushing mechanisms for all the E2 reactions below. So let's lock in. I got my mango juice here ready, so let me take a sip. I got the Simply Mango. Tastes like water. Don't get it. So, what's the first thing that you should do? Well, if you're an A+ chemistry student, Ochem student, you would know, well, the first thing you do is look at the base. And in your mind, you should be asking yourself, is this base just a regular old base, or is it a fat, bulky base? This tert butoxide is a bulky base, and this matters. And you're probably asking me, how do I know this is a bulky base? Well, I just made an E2 mechanisms video where I go over different kinds of bases. So, hint, hint, wink, wink, watch that. So, now, in all seriousness, why is this important? Well, when you do E2 reactions, most of the time, not all the time, but most of the time, you get 2 different products. You get the Zaitsev product, and then you get a Hofmann product. Okay? The Zaitsev is the more substituted alkene. So when you get the product, you make a double bond. So the whole E2 mechanism is you use a base, and what you do is you steal a proton, in exchange you put a double bond on the molecule, an alkene essentially, and you remove the alkyl halide. When you place that double bond, the one that has more branches coming off the double bond or having more R groups on the double bond on alkene is the more substituted one, and that's the Zaitsev product. So it's basically more R groups attached. Okay? The Hofmann is less R groups attached. Okay? This will make more sense when you actually do it, if you don't understand this. That's the first 2 things that you need to know. The second, third, and fourth thing is major and minor. Major, and then minor. The major product means that when you do this reaction, so you say you put all this stuff and you throw it in the beaker, and you get the product. Well, you get 2 different products. The one that is more abundant in quantity is the major, and then the one that's less abundant in quantity is the minor. You're probably wondering, how do I know what the quantity is? I'm going to tell you. Most of the time, when you do an E2 mechanism, the Zaitsev is the major product. Most of the time. And the Hofmann is usually the minor product. So you usually, when you do the reaction, most of the time, the more substituted alkene you're going to make more of. And the Hofmann, the less substituted one, you make less of. It's the minor. However, if you have a bulky base like tert butoxide, then it's flipped. Then the Hofmann product, or less substituted, becomes the major. So we make more of the Hofmann and less of the Zaitsev. That's why it's super important. All right. So let's do the problem now. The first thing you should do is look at the alpha carbon, identify where it is. The alpha carbon is the one that is it's a carbon directly bonded to the halogen. Okay, and this is an alkyl halide, right? Because this is a alkyl, so alkyl means carbon, and halide is halogen. So the next thing to do is identify all the beta carbons. The beta carbons are basically all the carbons that are attached to the alpha carbon. So this would be 1, this would be 1, and this one would be. And remember, the beta carbon has the hydrogen that we're going to sacrifice to make the double bond. So we have three options here. We have this one, and this one. You will notice that this beta carbon and this beta carbon are similar because look, it's a mirror image. Right? So you're going to get this and this if you create the double bond either here or here, it would be the same thing. So let's just work for one of them. Okay, so let's do the one on the right hand side. Okay. So these are the two beta carbons that we're going to look at. Let's do the top one first. So how do you do the mechanism? Well, what happens is the beta carbon must have a hydrogen. That is essential for this to work. If the beta carbon does not have a hydrogen, you cannot use it. So there's a hydrogen here. Tert-butoxide, the oxygen on tert-butoxide is what's going to do the reacting. So the electrons are basically going to go over and take it away to Epstein's Island or somewhere, okay? It goes bye-bye. Okay? So when this happens, the proton now is gone. It goes with the base. The bond between the carbon, the beta carbon, and the hydrogen now turns into a double bond between the alpha and beta carbon. So whenever you do an E2 reaction, the double bond always forms between the alpha carbon and beta carbon. So let's draw that in. Like that. Now you'll notice that the alpha carbon will now have 5 bonds. That's illegal. Because look at this. 1, 2, 3, 4, and now 5 from the double bond. So something must leave. And that something is always the halogen. It's the alkyl halide. So we basically delete this from existence. It's still there, but it's gone. Okay? So what we're left with is, let's see if I can just copy this. Ooh, paste. Okay, we're cooking. So what happens is, first we delete the halogen. That's the first thing you do. And get rid of this. Okay. This goes, and now we have to redraw this so it's geometrically straight, right? You can't have a bond going in this direction. You need to draw it straight. So that's what we're going to do. This is still the beta carbon. And remember I said that the double bond always forms between the beta and alpha carbon? There we go. And that's the answer. That's one of the answers. So let's do the other one now. Let's do the other beta carbon we talked about. So let's get rid of all this. And let's look at this beta carbon now, right? This one has a proton, which is great, so we can use this. So tert-butoxide, the oxygen is going to go attack this and basically assassinate the proton, like a hitman or a sniper. And once again, the bond between the beta carbon and the hydrogen now becomes a double bond between the alpha carbon and beta carbon. So let's draw an arrow to indicate that. And now the alpha carbon would have 5 bonds, right? 1, 2, 3, 4, and the double bond 5. So something must leave, and that's always the alkyl halide. So we draw the arrow to show it leaving. So then what we're left with is, let me just copy this. That, and then delete this. That, and then there we go. And that's the answer. That's the other answer. But this is still not complete because we're still missing some stuff. And it's always essential to include what left? Fluoride left. You need to draw in the electrons. Like that. And then what happened to the proton? Well, tert-butoxide took it. So what happened? Well, it becomes T, which is tert, butanol. Okay? So replace the K with an H. That's all you're doing. This is supposed to be a plus. Okay. So tert butanol. Now the main question. Which one is the Hofmann product and which one's the Zaitsev product? So here's how we do it. We look at the carbons here. How many branches does the carbons have coming off of it? So we have 0 branches here, right? So this is a carbon and this is a carbon. So 0 branches here. We don't count. We never count the alpha and beta carbon bond. That does not count. It's going away from that. So the beta one has nothing, right? There's nothing here at all. Alpha has 2, 1 and 2. So let's write that in, just for memory, so we can catalog it. 2. This one, so let's look at the alpha carbon first here. We have 1 and we have 2. The beta has 1 here. So that's 3 in total. 3 branches coming off of the double bond. 3 beats 2. 3 is bigger than 2. So 3 is the more substituted product. So this is the Zaitsev product. And then this is the Hofmann product. Now this is why I said it's really important to know what base you have. The reaction, so whenever you do this reaction, the outcome is always the same, right? No matter if I use sodium hydroxide or the mechanism is going to be the same. But what we do is when we categorize major or minor, that's where it matters. So we're using a bulky base. Usually by default, Zaitsev is the major product and Hofmann is the minor product, but since we're having a bulky base here, the Hofmann is the major product. We're going to make more of the Hofmann and less of the Zaitsev. This is the minor. And that's the answer. That's how you do it. All right, let's do this one. Our base is sodium hydroxide. This is not a bulky base. So by default, the Zaitsev product, the more substituted product, will be our major product. All right, first thing, find the alpha carbon. The alpha carbon is the one directly bonded to the halogen, right? This is the carbon directly bonded to the halogen. The beta carbon is everything surrounding, all the carbons that are attached to the alpha carbon. We have this one, and then this one. You will notice that the beta carbon, this one and this one are similar. So it really does not matter where I do the reaction. So let's do it on the top here. So we're going to use this carbon, the beta carbon, and this beta carbon. So let's do this first. Let's do this one first. So the beta carbon has the proton, which we're going to sacrifice. So sodium hydroxide, remember sodium never does anything. Sodium hydroxide, so the oxygen has the electrons. It's going to steal the proton, kidnap it away. We're never going to see it again. The double bond forms between the alpha and beta carbon. And now carbon has 5 bonds, which is illegal. 1, 2, 3, 4, and the double bond making 5. So something must leave. The alkyl halide leaves. And now we can draw the product. I should have copied this before. It's what the hell? Okay, I don't know. Come on, you can do it. You can do it. Come on. There, yay! You did it. Okay. So we get rid of all the first. Let's get rid of all the arrows. We delete the alkyl halide from existence. No, it's no longer there. The proton goes away. We delete that. This is not geometrically sexy, right? You can't have something going straight on at an angle like this. You can have a single bond going like that. So let's redraw it. That, and then this is the beta carbon. And so I said the double bond forms between the alpha and beta carbon. So let's do that. Like that. Okay, that's the first answer. So now let's do the second one. So the other beta carbon would be here that we're looking at. So this one does have proton. So the electrons from the oxygen are going to go and attack it. The double bond breaks and goes over to the alpha beta bond here and makes a double bond. Alpha carbon now has more than 5 bonds, but that's not allowed. 5 bonds, so that's not allowed. So this goes over. This. Okay. And now let me fix this up. So we are looking at this beta carbon. So the double bond forms between the alpha and beta carbon. So let's draw that in. Like that. And now the leaving group is iodine. So we need to draw that in. Don't forget it. So plus iodine with all its electrons. Okay. Now sodium hydroxide has stolen the proton. So what do we do? How do we write that in? Do we write plus? Plus. Sodium does nothing. It's never there. It's just the hydroxide. So the hydroxide, when you add a proton to hydroxide, it becomes water. So it's H2O. Okay. Now, the question is which one's the Zaitsev and which one's the Hofmann? Let's look at it. This has 0 things coming off of it, 0 R groups, so nothing there. The alpha carbon has 2 branches, 1 and 2. So let's write that in, 2. This one, the alpha carbon has 1 branch and 2 branches, and the beta carbon has another branch here. That's 3 in total. So, 3. 3 is higher than 2. So this is indeed the Zaitsev. And this is the Hofmann. Which was the major and which was the minor? Well, since this is not a bulky base, by default, the Zaitsev is the major. That easy. And this is the minor. There we go. Okay, let's do this one. This one's a challenge, by the way. It's a secret. See if you can get this one. Okay. First thing we realize is terpbutoxate, a bulky base. So that means the Hofmann is going to be the major product and the Zaitsev will be the minor. So we have alpha carbon. And we have beta carbons here, here, and here. Here is the thing though. Where do you put the double bond? All these beta carbons are identical. This is why it's really important to know your geometry. They're all identical. So what do you do? Let me take a sip of my drink. Well, let's take a look. If we put the double bond here, right? Okay, that's fine. Now take a look. I delete that. I put it here. It's the same thing. It's the exact same thing. Because remember, it's a mirror image. Same thing. Now, if I put it here, it's actually still the same thing. Because remember, these groups right here are all. Oops, let me do it a different color. So this is the same group. This is all the same. This is all the same group. When they're all the same group, you don't have a Zaitsev and a Hofmann. You only have one answer, and you can pick whatever you want it to be. So you can have it like this, right, like this, or you can put the double bond here, or you can put it there. Really does not matter. But let me just show you the mechanism. Terpbutoxide. is going to steal the let's go for the bottom one here. So let me draw the proton. Tert butoxide, the oxygen is going to steal the proton from here. The alpha beta bond becomes a double bond, and the alkyl halide leaves. So we got that's ugly, but you know what I mean, right? Okay, that's the answer. Plus the bromine. Okay, like that. And then this becomes tert butanol. So plus T butanol. And that's the answer. That's it. So whenever you cannot make the Zaitsev Hofmann, you can pick whatever you want and then just draw in the product plus the halogen, and then the base with the proton on it. All right, for each of the problems, tell me if you would use a hydroxide or tert butoxide to achieve the desired product. All right, so we're only going to use two different bases, right? Either hydroxide or tert butoxide, according to the question. Hydroxide is not a bulky base. Tert butoxide is. So hydroxide will give us the more substituted alkene, and tert butoxide, since it's a bulky base, will give us the least substituted alkene, or less substituted. So let's look at the first one. Here we see we have this original molecule, and then we get this final molecule. You will notice that this alkene has how many substitutions? Like how many R groups does it have? It has 1, 2, 3, 4. You cannot get higher than 4. 4 is the max, right? Because this carbon can only have 4 bonds, and this carbon can only have 4 bonds. So 1, 2, 3, 4, and this carbon 1, 2, 3, 4. So you can't attach any more R groups to this. It's already as substituted as it can be. And since I said that hydroxide is all about more substituted, right? More substitutions, more R groups, we know that it's going to be a hydroxide that is going to be the base. Okay, what about this one? Here, we have this bromine, and this entire molecule with bromine, and then we have this final molecule here. The double bond is located here. You'll notice the substitution is 1, 2. 2 branches. Okay? So let's look at all the other possibilities where we could put the double bond. So this is the alpha carbon. This is beta, and this is beta. Well, if we were to put the double bond here, it's basically the same thing as here. It's the same molecule, right? So if I put the double bond here, it's the same thing as putting it here. So the only other option is putting it here. And if you take a look, how substituted it is, how many R groups does this alkene have? Well, it has 1, 2, 3, 4, and 5. And then since that's illegal, we have to kick out the alkyl halide. So if we eliminate this, now it has 1, 2, 3, and then 1, 2. So it is already very substituted, right? It has 4 substitutions if you were to 4 R groups if you put it in this configuration, right? Very substituted. Unlike if I were to go and put it here, that's not substituted. It's only how many branches, right? Only 2 branches, 1 and 2. And that's what we're looking for. So compared to the other one, right? We would use tert butoxide to get this because this is the less substituted version of this. The more substituted would be putting the double bond here. And that won't work because you would need hydroxide for that. So that is the answer. That's how you do those. All right, challenge. Adamanidine is a strange bicyclic structure. The composition is very similar to the structure of diamonds. It's actually found in petroleum. So imagine that the derivative of diamonds is actually in gas for your car. Given the reactant and base, predict where the double bond will form. Okay. So this is the actual structure. I just added bromines to get this done, right? To get this E2 reaction done. First thing you realize is you have tert butoxide. So the Hofmann will be the major product. We're looking for something that's not substituted, right? We have two bromines here. Which bromine do you think is going to lead? Here's how you know. Because you have to, this is why you have to be careful, because your professors may trick you. If you're looking at this bromine, right? This is the alpha carbon, and then this is the beta carbon. So we only have one beta carbon. But look at this. This carbon has 1 bond, 2 bonds, 3 bonds, 4 bonds. There are no available protons to steal. The base cannot steal any protons because there's none there. So no matter what, this is not going to participate. So this alpha carbon, this beta carbon will not participate in the reaction. So this bromine is not going to leave. So that basically leaves out the bromine here. So we have this. So this is the alpha carbon. This is the beta. This is the beta, and this is the beta. Okay? There is a rule that you may not know. It's because I haven't spoken about it yet. I will now. There is something called Brent's rule. Brent's rule states a double bond cannot form inside of a ring during elimination reactions unless the ring is really big, really large. In this case, it isn't. Just take my word for it. It isn't. 99.9% of the time, it's too small. So it is actually illegal for a double bond to form inside a ring like this. So it's not allowed due to Brent's rule. He just discovered it. He asked him. He's long dead, but you know. So is here, right? Alpha beta bonds, right? We double bond, right? You have a double bond between alpha and beta, but we can't do this because it's inside the ring. So the only option here, like that. That's the only option. So that is the answer. So what's going to happen is this beta carbon is going to participate, but these cannot. Kidnaps it. Double bond forms between the alpha and beta carbons, and this leaves. So we get copy. Okay, delete arrows here. The alkyl halide leaves. This, and we get ta-da! And that's the answer. If you found this video helpful, please like and subscribe. Until next time, later.